Yeah, this afternoon we're going to talk about, well, I think this is not the, we're going to talk about what we call absolute value equations, right? But before we can get to the equation, um, we just have to be introduced. I think I did introduce this function last week when we did functions and graphs, right? So I'm just going to reintroduce it again, the absolute value function, right? And it's, as I said, it's a good introduction to what we call piecewise function, where different pieces of the function is defined differently, right? So for certain parts of the domain, you define the function by some expression, and then another part of the domain, you define it differently, right? When you do calculus, you see a lot of that. So this is a good introduction, right? So as we said this here, I think I have to go up here to do what? What did I do? I have to come up here. I think I have to. Yeah. Yeah. So what you're seeing here, the function, when the value of x or the domain values are positive, right? Zero and positive, well, the range is positive as well. When the domain is negative, that's less than zero, well, you simply change the output. Well, you change the value of x to minus, meaning you keep it positive, right? So if you have -1, you take the positive of it. -2, you take the positive of it. That's what this means. Minus x. Remember, x is negative. So you just take the positive of the number then, right? And that's why this part of the function, you see that it's still positive, right? It's still positive. So even though x is -1, y is +1, right? +1. Even though x is -2, y is +2, right? So this is a good example of a function that is defined piecewise. That's the word we use, right? For the negative values of the domain, we define it to be -x. And for the positive values of the domain, well, it's just x, right? Or the same value as the x value, right? This is an alternative definition of the function. It's the positive square root of the square of the number, right? So like you take -1, right? You square it and you take the positive square root. So what you find is the modulus of a number, right? The modulus of a number x cannot be a negative, cannot be negative, right? Cannot be negative. The modulus of a number has to be either zero or positive. Keep that in mind. Good. So now that we've been introduced to the function, um, they have equations that involve the modulus now, and that's what you have to know how to solve. That's what you have to know to solve. So let's look at what they look like. Can I get this fell out here? It's cluttering up my. Good. So when it comes to an equation that um, is an absolute value equation, you're making use of either of these two definitions, really, right? We said that um, I think something is wrong here. B can be zero. I think B can be 0. What am I doing here? Yeah. I think B can either be 0, it can be 0, right? The modulus of a number can be 0. It can be negative, right? So if the modulus of some number is equals to B, then either, we're saying P, right? We're calling this any number P. If the modulus of P is equals to B, then either P is negative B or B. Think about it. If you have, okay, negative B, the modulus of negative B will be B. The modulus of B will be B, right? So if the modulus of a number is B, then the number is either minus B or B. That is what all of this is saying. That's what all of that is saying. And then we also got this definition that the modulus of a number is the positive square root of the square of the number. Right? So we're going to use those two facts to solve any equation that involve the modulus. And they got all kinds of queer ones. Eh? Oh, I think there's a mistake here. I did this work so many years ago, and sometimes I would correct myself in the class, but I never, because you can have 0. The modulus of 0 is 0, right? You can have that. Yeah. So let's take this one. You have to solve this equation. What's it? 2x minus 5. The modulus of 2x minus 5 equal 9. Right? And I think we're going to see two different approaches. Right? We're going to see two approaches to the whole thing. This is one approach where we said, okay, we're going to let 2x minus 5, the positive of it. Right? Remember we said, if the modulus of P is B, then P is either equal to minus B or P equal positive B. So that's what we're doing here. So we're going to take 2x minus 5 equal minus 9. We're going to take the minus for us, right? And then you solve that, because this is basically a simple equation. You don't have to ask me how to solve that, right? You can solve that. Or 2x minus 5 is equal to positive 9. And then we solve that, and we get two answers. Right? So you put what's in the modulus there equal to the positive of this and then the negative. But I think I did the negative first, then the positive. Right? Moving from left to right. I go from the negative, I use negative 9 first, and then positive 9. And in both cases, what you have here, this is a simple equation, and this is a simple equation, right? So I don't have to show you how to solve that. It's the idea I want you to get over, right? Once you get the idea that, okay, if the modulus of this expression in here is equal to 9, then the expression is either equal to minus 9, right? Because if the expression is equal to minus 9 in here, the modulus of that is 9. Or the expression is equal to positive 9. The expression in here equal to positive 9. So the modulus is also going to be 9, right? And that's why we put the expression in the modulus sign equal to minus 9 or equal to 9 itself. And we take those two and we solve them. And you get two solutions. Minus 2, 7. Right? So that should clarify that, right? Am I going too fast? If I'm going too fast, you just slow me up.
Sir, I want to ask, is it like the x equal negative 2 and x equal 7, right? I thought it was you take the number that is either 0 or more than 0.
No, this is not a quadratic we're solving. I think you're stuck at quadratics.
No, sir. Like you see, it's if P equal B, B is more than or equal to 0.
No. This is just saying the number outside here has to be a positive number. Sorry, it has to be either 0 or positive. If I give you, I remember when I was a kid going to UG, and the lecturer put up a question like this. He put something in here, and he put it equal to -2, right? And he asked me, solve this, right? And I was trying to solve the thing. The man said, I fail you. He's a Cuban guy. He was very brash. The man said, I fail you for that because I was attempting to go and solve the thing. And by the way, if you try to solve it, the mathematics will give you a number, an answer. But you should know that a modulus cannot be equal to a negative. You don't have to even solve that. You have to just say, sir, no, that is not a problem that could be solved. Because the modulus of a number can't be negative. You get me, the money?
Oh, oh yeah, yeah, sir, I understand.
B
I
can't be
thought you was
negative.
talking
So
about the result.
no, not the answer at the bottom here. This can be all kinds of numbers because when you put that in there, remember it's 2x minus 5, right? So there's something to be done with this here. So you can't look at this and worry about nothing. You gotta make sure that the number out here, that's this number here, that's a positive number. So before you proceed to solve any any absolute value equations, make sure that it's equal to a positive something, right?
Okay, sir,
If
thank you.
not, don't proceed. Don't proceed. Somebody trying to fool you, right? And I can tell you, I like to tell stories of when I was wrong and coming up. I'm often wrong. That's not a problem. Being wrong is never a problem. Good. So let's go to the alternative approach, right? So we're using this now, this definition here. The modulus of P is equals to the positive square root of the square of the number, right? So we put back our equation. And this is heavy algebra now. So instead of writing 2x minus 5, we're using this definition here. So we're putting that as the square root. And I didn't write the positive square root here. I think it's understood, right? So I don't have to write the plus sign there all the time, right? Once I don't put plus and minus or minus, you know I'm dealing with the positive square root, right? Good. So I'm writing the modulus of 2x minus 5 as 2x minus 5 square, the square root of that, equal 9, right? So the square root of 2x minus 5 square. Good. The obvious approach to use after that is to square both sides, right? Is that what you do? Square both sides. So squaring both sides would kind of get rid of this square root sign, and you get a square on the 9. You get it so far? Right? Very simple. And then, well, you can use difference of squares. That's what I did here. I brought the -9, the 9 square over the equal sign. So you have a difference of squares there. And I can use the difference of squares. Okay, I kind of missed it out. Let me show you what I did. Down here, I have this 2x minus 5 plus 9 times 2x minus 5 minus 9, right? So that's what I did, right? See if you agree with me. When you have a difference of squares, it's this plus that, and that's how I get 2x plus 4. And 2x minus 5 minus 9 will give you 2x minus 14, right? And you get that. Let me erase it because the answer is going to come up there. And I think you get the same answer, right? Yeah, you get -2 or 7. So regardless of which approach you use, you're going to get the same answer. I'm going to allow you to digest, see if you get it. I know this step here, I got to jump. Uh, I kind of jump out a step there. There was a time when I have some very sharp students that you don't have to fill all the steps in, man. You know, they get it. And sometimes I like to puzzle you a little because that's the only way you'll do some thinking. And how this guy get his thing, man? How he get his thing? So you will remove the bracket and then factorize and all of that. You don't have to do that, right? You don't have to do that. Good. Let's do a last example. Oh, I don't think this is the last one. Okay, let me go with this one. So you have to solve this one. What's this? X minus 2 equal 3x plus 1, right? So you follow the same procedure. You follow the same I don't think I did it both ways. Let me see. Let me see. Yeah. So you just take what's in the in the modular sign there, x minus 2, put it equal to the minus of this. That's what you see here, right? If you remove the bracket, you'll get this. So you have x minus 2 equal minus 3x minus 1. And you can solve something like that, right? Let me not insult your intelligence. And you will get that. I'm not going to show you how to do that. And the second step is that you take x minus 2 and put it equal to positive 3x plus 2, 3x plus 1, which is the same thing, right? You don't do anything this, and then you solve, right? So one time you put it equal to the minus of this, minus of it. And the next time you put it equal to the same thing. Don't change nothing. And you solve. That shouldn't be difficult. Don't get scared now that there isn't a number there, right? That there isn't a number. However, I think there's a word of caution here. Because there is an x here, it is possible that one of the values that you have here, one of the values that you have there, will make this side negative, right? Maybe when you put, I don't know, maybe this one here, minus 3 over 2. If I put it here, when I work out this whole thing, you have a negative. And I told you the modulus of a number can't be negative. Let's see what happens. And look at what my suspicions are right. Look, the quarter isn't a problem. 3 by a quarter is a positive number. Plus 1 will give you a positive number. No trouble there. So when you use x equal to a quarter, you have no trouble. Star. Get it right. But note this one, right? Note this one. So I'm going to try minus 3 over 2 in the place of x there, which I'm doing here, right? Okay, no, over here. 3 times minus 3 over 2 plus 1 gives you a negative number. You see? You get a negative number there. And therefore, remember I just said, the modulus of a number can't be negative. Therefore, this here is an invalid, it's an invalid solution. Right? You see, so funny thing, the mathematics, you put the thing equal this and you solve and you get an answer and you start rejoicing. Right? The mathematics is very much like a computer. Sometimes the computer gives you something, but it's stupidest. Sometimes the AI does it. Right? You go on YouTube and you find a video of people talking about what's it stupidness. You understand? You gotta test it now. You gotta test it. And there's where your knowledge that, okay, you know what? The modulus of a number can't be negative. And that's what you're seeing here. So it's going against the basic definition of the modulus of a number here. So your answer is x equal to a quarter. That's your only answer. Your only valid answer. Right? So be careful. So this one is tricky. All right. Let's take another one. Want to digest it a little? Let me leave it there. for a moment. I didn't do it with the alternative approach. You could try it, right? I don't have to do everything for you. You could try it with the, using the thing where the modulus of P is equals to the positive square root of that, right? Try it with this here. The algebra is going to be a little more heavy, right? But you can try it, right? Never feel that, you're looking for the easy way out. Let me see the easiest way I can solve this problem, right? That can get you into trouble. Granted, we're looking for efficiency and all of that, yes. But never think that, well, doing things the hard way is, it's a waste of time every time, right? Sometimes it probably tests your algebra skills, right? It puts you to think along different lines, right? So, no, don't be afraid. Don't shy away. Don't think it's a waste of time. As a matter of fact, even, I tell students, if you have a maths problem and any problem, and you're not able to solve it, but you're trying all kinds of approaches, don't think that the time you took to try those approaches is a waste of time. No, it's a learning experience. You learn a lot of stuff. I think I told you this before, or probably I didn't tell you. When Edison was trying to find a filament for the light bulb, right? Well, of course, look where we are today. We don't use no a filament for no light bulb, right? Did the man waste his time? No. He found a solution that lasted for hundreds of years, right? Well, I shouldn't say hundreds, but I mean over a century. What he found worked, right? I don't think they make filament bulbs much, maybe for special purposes. No, but anyway, he tried a lot of things. Story has it, right? And I know these things can't be verified easily. That the man tried up the grass. He tried grass, right? I remember one movie I'm watching, and the guy said Edison tried about 1,000 different materials, but what he found out at the end is that he knew what wouldn't work, right? Sometimes knowing what works, yeah, it's important, but knowing what wouldn't work is also important, right? It adds to knowledge, and you never know. Somebody is going to come along and want to go down that line and says, no, 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 I already tried that, it doesn't work, right? I mean, I have to bore you with all of that. I think I have to erase all of this because it's going to show up. What's this now? It's going to show up on the next slide. Again, I think it's an exaggeration when they say he tried over 1,000 different materials. I doubt that he did that, All right, I think this is the last one. So we have the modulus of something is equals to the modulus of something, right? Good. So what do you do here? Well, you do the same thing, basically, right? But here what you do. Because over here it's also in a modulus, right? So what we're doing now, we're taking the 2x minus 1, put it equal to the minus of this, which you see here, right? And then you take 2x minus 1 equal to 4x plus 9. We use the negative one time and the positive. The reason why is that, okay, if you were to put, okay, let's say, all right, you were to put a minus over here and a minus, it will cancel out, right? So we take the positive here, 2x minus 1, put it equal to the negative of this, and then we take 2x minus 1 equal to the positive, right? And these are your two solutions. In this case, you don't need to check for nothing because regardless of what x is, like this one is a suspect. Who is talking there? Somebody needs to mute themselves. How do I get them to? Yeah, Julian Day, you need to mute yourself, by all your business we're hearing. He probably don't even know I'm talking to you. Oh gosh, participants. What the hell is this? Here, I know he is not near the computer, right? Because if I'm talking to him to mute his mic and he doesn't hear me, it means he's in the yard walking around. I think some of these people who say they get blackout, they're actually at the what do they call it, Christmas party at the school. All kinds of things you see in this job. Yeah. Yeah. So you put it equal to the negative of what's in there, and the next time you put it equal to the positive of what's in there, right? And it works. The alternative approach would have been to, I don't have space to do that. If you were to use the other approach where you put 2x minus 1 equal to, well, okay, put a square equal to, remember I'm jumping some steps here, plus 9 square, right? And then you take it to one side, you get 2x minus 1 square minus 4x plus 9 square equals 0, huh? And then you let me bring this down here, bring the action down here. So you get 2x minus 1 minus what's in here. So you get minus 4x minus 9, put I in one bracket, times 2x minus 1 plus 4x plus 9, right? Equals 0. And you get what in here? Oh gosh, you get some horrible numbers in here. 2x minus, okay, minus 2x. Minus 1 minus 9 is minus 10. That's not a problem. You don't worry about that. We're not looking at looks here. 2x and 4x is 6x. I hope I get the right answer with this. Minus 1 plus 9 is what by positive 8 equals 0. So yeah, so from this, you're going to get minus 2x equal to 10. Oh, that's this answer here. And this one, 6x plus 8, you get that, right? You will get that one. Yeah, so you will get the same answer. That's the alternative. Right, so either you go this way or you use the difference of squares thing to get the answer. So I think you get a knack of, you should, I should say, right? Get a knack of how to solve these equations, right? What we're going to go to next is some inequalities now, and we're going to talk about, well, maybe I could start with absolute value inequalities, right? I could probably start with that. So I may, let me pause the, because I have to do some transition. So, right, pause the recording. Yeah. Good. Yeah, so I think this should bring us back where we left off, right? So we're looking at absolute value inequalities now. We talked about the equations just now, right? And here we are. We want to deal with inequalities, dealing with absolute value expressions now. Something that is we're finding the absolute value such that it's probably less than or greater than something. So let's start with the one where, all right, the absolute value of something in there, right, is less than or equal to, well, some given number. Well, they're using a number, to start with. Let's see if I can annotate here. Yeah. Let me move this fellow to the, yeah. So if some number, the absolute value of it, is either less than or equal to 4, then the number must lie between -4 and 4. Think about that. So we got a number line here, right? And minus 4 is here. Let's go with 0 there. Let's go with 4 here. So if the modulus, and remember the modulus basically is the length of the line segment from 0 to that number. So P, if the modulus of P is less than or equal to 4, then P lies somewhere between minus 4 and 4. See if you agree with that. Because any number between minus 4 and 4, well, in this case, they have an equal sign here, so inclusive of minus 4 and 4. Any number between there, the modulus of it is going to be either 4 or less than 4. You agree with that?
Yes, sir.
And that is why they came with this general, look at this general condition here that if I don't think you need to memorize two things. The only difference here is this one has an equal sign, this one doesn't, right? Just be conscious of that. If you start off with an equal sign there, well, you keep it throughout the problem. If you don't have one there, don't use it, right? So you don't have to memorize two things. It's one thing, right? I also disagree with what is it? B doesn't have to be greater than 0. It could be 0. It could also be 0. I took these notes to somebody from the internet, Every year I have to correct myself. I need to probably discard these notes maybe this year and let the AI give me notes or something. Everybody's taking things from AI. Why am I using these antiquated notes? Yeah, it doesn't have to be greater than 0. It could also be equal to 0. Right? You could have an inequality being, B can be a number 0, 2. That's not a problem. Good. So basically, that's a condition you want to keep in mind. That if the modulus of a number is less than, let's say, okay, you go with this, less than B, then that number is between minus B and B. That's all you have to remember. The only difference in this statement here, there's an equal sign here, right? So, down here. This equal sign here, right? Here and here, right? That's all. So once you know this condition, you can solve any absolute value inequality using it. All right, let's go to an example. Right? So here we have it that you have to solve 2x minus 4. The modulus of 2x minus 4 is less than 10. So the condition, we're applying this condition here. We're applying the condition you see here, right? And we're putting 2x minus 4 is either greater than minus 10, but less than 10, right? It's somewhere between minus 10 and 10, right? So it looks like that. And I know you probably never saw an inequality like that, but you don't have to worry, right? You want to get rid of this minus 4, so you add 4 throughout, right? So you add 4 to minus 6. Minus 10, you get minus 6. You add 4 to 10, you get 14, right? So adding 4 in the center will give you the 2x, yeah. Adding 4 to minus 10 gives you minus 6. Adding 4 to 10 gives you 14, right? And then you divide throughout by 2, and this is your answer. Nothing should bother you there. Just remember this condition, right? This one, or if you want, when there's an equal sign involved, you just put it there, right? Like an equal sign here. This one doesn't. The next one will have one. The next example. Oh, I think I have to erase these things or they'll show up here now. Good. So look at this one. You have to solve modulus of 3 minus 2z is less than or equal to 5. Right? So we apply the condition, right? We're applying the condition here, right? So we're writing 3 minus 2z is either greater than or equal to minus 5, but less than or equal to 5, right? Meaning 3 minus 2z is somewhere between minus 5 and 5, right? It could be minus 5 and 5, but otherwise it's somewhere between these. And we do the necessaries again, right? You want to get rid of this 3, so we minus 3 throughout. So minus 5 minus 3 give you that. Take away the minus 3 from there, you get minus 2z. And then you take away 3 from there, you get 2, right? Now you have to divide. You have to divide by minus 2, right? Now remember, when you divide by a negative number, what do? You have to turn around the inequality sign, right? You have to turn around the inequality sign. I don't like how this one is written. What I'm supposed to have here is, okay, if you turn around this inequality sign, you get this, right? And you turn around this inequality sign, you get that. So you can write this as z is greater than or equal to minus 1, but less than or equal to 4. Right?
Yes, sir. Yes, sir.
Yeah, I don't like how this one. I think I probably caught this from a textbook or somebody online some years ago. Uh, so I'm going from left to right, from negative to positive. Good. So we got that, right?
Yes, sir.
All right, good. We're going on to if the inequality sign is the other way around, right? Like this then. The greater than sign, not the less than. Oh, what did I do here? Good. So here we have another kind of an intuitive example. So we have the modulus of some number p is greater than or equal to 4. Now, if that's the case, they're saying that either p is less than or equal to minus 4 or greater than or equal to 4, right? And again, if I'm to use the number line to illustrate that. So if the modulus of a number, all right, let me go with minus 4 here and 4 here, right? And the modulus of p is greater than or equal to 4, right? So p can be between here. It can be between there because no number between here, the modulus of it is greater than 4. P has to be a number outside here or a number outside here. That's what that is saying. That's what this is saying, isn't it? P got to be something like minus 5 and minus 6 and minus 7 and so, or 5, 6, and so on. It has to be outside of that interval, minus 4 to 4. Right? And that's where they got this from. That P has to be either less than minus 4 or P has to be greater than 4, right? Generally, we can do this then. We can write this. We can say that, look, if the modulus of P is greater than or equal to B, then P is either less than or equal to minus B, or P is greater than or equal to B, right? And don't think of these two things as two things to memorize. This statement has an equal sign there, this one doesn't, right? So you don't have to memorize two things. Just keep that in mind. Just remember this. Once you remember one of the statements, that's all. No need to memorize two things, right? And that's another thing about memory. Yeah? Whenever you want to remember things, you want to develop some kind of system, right? I don't know. I hope all of you have some kind of system when it comes to remembering things. Don't just use brute force and cram the thing as they say, right? Sometimes you can develop a system to remember things, right? Um, some people, they can. Some people. Does anybody like talk things aloud?
Yes,
Anybody, when to
sir.
remember something, you speak it out aloud?
Yes, sir.
I locked the door. And it might feel stupid, but feeling stupid helps, right? Feeling stupid helps because when you go on the road and you forget that did I lock the road? Yes, and I laugh myself when I say it. You remember that you felt foolish when you did it, and that's what some people. I'm gonna tell you this here. I remember seeing a documentary one time, and they were talking about trauma. That if you were traumatized by something, like maybe okay for the girl, somebody tried to. Oh gosh, I shouldn't even use the example. Let me say somebody attack you. I wouldn't use the word rape. Somebody trying to attack you. It's very traumatizing. And you tend to remember the incident. It affects you sometimes your whole life. You're like a little jumpy when people are behind you or people kind of come and touch you from behind. You get jumpy. You never forget the incident. And basically you're traumatized by it and it's embedded in your memory. Right? So I used to make jokes one a couple of years ago. I said the reason why I traumatized some students is for them to remember things. They remember the man got here, the man give me not for the thing. I'd never forget. I'd never forget a problem because I get not fit. Well, at least you remember it. Of course, people do all kinds of other things, right? So I'm just joking, right? But if you develop a system for remembering things, um, you tend to remember it better, right? As I told you already, note taking, taking notes. Your brain remember you writing this thing, right? And another thing about note taking, sometimes I talk so much, or a lecturer is talking so much, but you can't write everything the lecturer is saying. So your brain is forced to summarize, and before you can summarize, you have to understand. So because your brain now is pressured to say, you know what, you're trying to understand, and that's why some of you sit down, you wouldn't ask a question. But sometimes you have to say, stop. I ain't get that. I ain't get that. Could you rephrase that? Could you put out a different way for me? You know, you understand? Some teachers would actually encourage memory and say, all right, tell me what you understand. Your teacher ever do that to you? I don't ever do it because y'all are, I should ask you back, all right, tell me what you understand by this thing. And then you realize people don't understand nothing at all, right? So that's why note taking. You have to summarize what is being said. For you to summarize, you must understand and you must be able to express it. All of that fosters memory. You understand? Those are most people, I think, of all of you in the class, most of you just sit there and you're waiting for the recording. Nobody's, or few of you are actively taking notes and analyzing. And that's the next thing. That's the next thing that fosters memory. Active listening, right? Comparing it. So I say, wait. I learned this in you know, primary school or I learned this in high school, but I didn't get it. So I wanted this man telling me the right thing, or I got the right thing in high school, and all of that. You understand? So active listening is very important. Don't just sit there passively, and say, man, already, man, me get time with tea, I got me pot on the fire, or I got me TV show on, and and stuff going on. No, you're gonna watch the video later. You're wasting time. Why were you here anyways? Good. So let's use this. Let's use these properties here to solve an inequality. So look at this simple one. The modulus of 2x minus 3 is greater than 7, right? So it's either we said 2x minus 3 is less than minus 7, or 2x minus 3 is greater than 7. These are two linear inequalities. I don't have to solve them for you, right? It's just getting the property right, right? That if 2x minus 3 is, the modulus of it, sorry, is greater than 7, then 2x minus 3 is either less than minus 7, or 2x minus 3 is greater than 7. That's all you have to remember. When you're dealing with a greater than sign, you have two pieces there, and you have to solve one or the other. And you solve, right? I shouldn't have to go through anything there. Take another one. You have the modulus of 2 minus 6y is greater than 10. So you either have 2 minus 6y is less than minus 10, or 2 minus 6y is greater than 10, right? And you do your thing, right? Both times, notice you have to divide by a minus 6, so the inequality sign had to be flipped around, right? Here too, you just flip it around, right? Just be conscious of that. Sometimes you forget again how you solve inequality, right? We doing good so far?
Yes, sir.
Yes, sir.
The money, why? Yeah. Okay. So I have to pause again to go to. All right. Let me. Yeah. Good. So yeah, I think when I did used to teach this before, I would normally for some reason my rational inequality isn't showing up, and my absolute value inequalities isn't showing up. Something wrong with the compatibility of the programs. Anyway, good. Yeah. So when I used to teach this, I used to go from linear, then quadratic, then rational, then absolute value. But since we did absolute value equations, I said, let me knock out absolute value inequalities and done with it, Yeah. So we're gonna go back to, well, we did this before, linear inequalities, but we're gonna borrow some ideas, right? And then we go to quadratic inequalities, then we'll touch on rational inequalities, right? Good. So we all know linear inequality. What's going on here? Oh, that's a rational inequality. Oh, maybe I have to just click on next. All right, good. That's a rational inequality, meaning you have like something divided by something, like a ratio, fraction, And then absolute value, well, we did that before, right? We did that. We did this. So we don't have to go back there. Good. So let's look at a linear one. You all know this, right? You all know this. You all know this. There's nothing for me to explain here. You solve it just like you would solve equations, only if there's a division or by a negative number or a multiplication by a negative number, you reverse the inequality. In this case, this has nothing to do with that. There is no division or multiplication by a negative number, so there's no problem there. Good. But there's an idea we want to start introducing here. And you'll see it here, right? So, you know, this idea, I wonder why this thing is taking so long to change. Yes. So here we have the inequality, and I'm using a different idea to solve the inequality, right? And you wouldn't use it for a linear inequality, but we're going to borrow the idea and we're going to fetch it to when we're going to deal with perhaps the quadratic inequality, and especially when we're dealing with the rational inequality, right? So here we have, okay, we have the inequality to solve, right? And 1 second, get this out of the way, yeah. So we have this to solve. And what I'm doing, I'm trying to, I sketch the graph. No. Bring this 5 over here. So you get 2x minus 8, right? Minus 8. I sketch the graph y equal to x minus 8. That's the line here, right? That's it there. And when you look at 2x minus 8, you notice that the line crosses the x-axis at 4. And I don't know if you're seeing the number 4 here, where 2x minus 8. If I'm to put this equal 0, you get x equal 4. And this is what we call like a critical value, meaning that the behavior of this function changes around 4, right? Or the output value changes around 4. And you see that here. You see that for numbers greater than 4, the inequality goes positive, right? While for numbers less than 4, the inequality goes negative, right? And you can already see that, well, you want, well, okay, 2x minus 5 is greater than, 2x minus 3 greater than 5 is equivalent to this. It's the same inequality, just written differently, right? And you can see that your solution then is this, x is greater than 4. Because when x is greater than 4, the function goes positive, right? Greater than 0. Positive means greater than 0. So that's your solution here. Now, you didn't have to do this. You know an easier way to solve this equation, right? This inequality. But we're going to borrow this idea, right? We're going to borrow this idea. So I have to erase everything here. Yeah, this is just showing you what I was just saying, right? Good. So look at this one. Same inequality, right? So I converted this to that. And I put the critical value 4. And I analyze how the inequality would operate less than 4 and greater than 4. Right? And what you see is that it is the region x is greater than 4 that satisfies the inequality. And we're going to borrow this idea just now. We're going to borrow it. And you'll see when you reach these complex problems, if you have to solve something like this, right? Don't ever use this idea. Don't use this. Don't use it. I am just using it to illustrate something So the harder inequality, you're going to borrow the idea. I don't know if you understand what I mean. Right? You're going to see in just a moment. I don't know. Oh my, what's up? Good. Let's go to this quadratic inequality. So you have to solve something like this. So okay, you factorize it. You get a sketch of the graph, and you'd have to know. You'd have to have some knowledge here, right? You'd have to know that okay, the graph cuts at -2. Notice is the opposite of this number here and the opposite of this one, right? So the critical values are -2 and 5. So you know the graph cuts here and there. And I guess from high school, you know that when there's a positive value there, the graph is kind of U-shaped. And there are some people who can actually read off and say that, you know what? This function is less than 0 for these x values. Right? So that's why I have here x is between -2 and 5. Some people can do that. Some people can't. Some people, for the life of them, they can't read this graph as to for what x values is this graph less than 0? For what x values is this graph greater than 0? They can't get it. I mean, I'm not saying, well, because they can't get it, find another method. I'm not saying that. They should understand why we're saying that for x between -2 and 5, the graph is negative, right? Or less than 0. Because watch. All right, let's take -1. -1, you come down here, you come down here, you come down here, you come down here. The graph is negative something, right? When x is 0, the graph is -9 point something, right? Okay, -10, sorry, -10. 1, you come down here, you come down, you come down, you come down, you come down. The graph is some negative number there, right? For all these values between here, the y value is negative, less than 0. That is why this is your solution set, right? For those who have difficulty with that analysis now, we're going to borrow the idea we just used. For some reason, I'm getting a pain in my chest. Thankfully, it's not in my my left side where my heart is. It's the other side. Yeah. So let's borrow from that idea I just showed you, right? So, all right, let's go to the next slide and you'll see what I'm talking about. Good. So here it is, right? So we have here, seeing a little blot there. I wonder why that is there. Yeah. So we take the quadratic expression, we factorize it. We get the critical values being -2, 5. So we mark them off and we divide the number line into 3 sections, right? We're looking at less than 2, -2, sorry. We're looking at between -2 and 5, and then greater than 5, right? And what we're going to do, we're going to analyze now what is the value of the inequality, right? Or how the inequality is behaving in this region here, in this region here, then in this region here, and then in this region here, right? So that's what we're going to do next. So we're going to take a value of x that is less than -2. We're going to take a value between -2 and 5, and we'll take a value here. And we're going to put it in this inequality and see how it behaves. You don't need the graph. No, you don't need a graph. You just need these 2 critical values, right? That's what we're going to do next. So note here, I took a number less than -2. I took -3. Put it in the quadratic, you get 8. 8 is greater than 0. Therefore, x less than -2 is not a solution. We don't discard of that, those numbers on the number line. Let's take a number from in between here now, right? Let's see what happens. So we take a number, we take 0. When we put it in inequality, you get minus 10. And minus 10 is less than 0. And therefore, we say, you know what? Numbers in this range can very well be the solution. And it is, right? So the numbers between minus 2 and 5 will make this expression x squared minus 3x minus 10 less than 0. And you can try any number between here. You don't have to proceed to this part, but for your own mind, for your own peace of mind, you can try a number greater than 5, right? And I use 6. Put it in there, and what happens? You get 8. And 8 is greater than 0, which is not what you want. So your conclusion, the numbers between minus 2 and 5 is the solution to your inequality. In this case, you didn't have to draw the graph. You just needed what we call the critical values here, right? And you divide up the number line into 3 sections, right? You don't even need the y-axis business here. You don't need that. You could just take the bare number line, the x-axis, and divide it up into 3 sections and analyze what's going on in each one of those sections, right? Anybody getting an idea what I'm doing here?
Yes, sir. Yes, sir.
So our conclusion, of course, is that x is somewhere, x between minus 2 and 5 satisfies the inequality, right? Good. Let's take another one. So you got this one. X squared minus x minus 6 is greater than or equal to 0, right? Good. So again, you factorize it, you get your critical values to be minus 2 and positive 3. So you don't have to sketch the graph. You don't have to. There are people who have that aptitude. They could sketch the graph. They could pick out the set of values that will satisfy the inequality. But for others, you can use this analysis. So again, we break up the number line. Okay, the numbers less than minus 2, the numbers between minus 2 and 3, and then the numbers greater than 3. And we're going to try numbers from each of these regions to see what happens, right? So we take a number less than minus 2. We take minus 3. Put it in inequality. It is greater than 0, right? So yeah, this region here seem to be satisfying the inequality. Let's take a number between here, right? We take, okay, we take 0 again. When we put it in the inequality, you get minus 6. And minus 6 is not greater than 0. So numbers between here does not satisfy the inequality, right? And then you try a number out here now, right? And we try, okay, a number greater than 3. We try 4. Yes, it works, right? When you put it in inequality, you get 6. And 6 is greater than 0, right? So therefore, the numbers greater than 3 also satisfies the inequality, right? Therefore, your solution set then is x is less than minus 2, less than or equal to minus 2, or x is greater than or equal to 3, right? They're two disjoint sets. So with this analysis, you didn't need to draw the graph, right? But there are, I think, from a lot of you who did CXC and so, and these things are fresh, you could do this without doing this analysis. This analysis will become useful when we deal with rational inequalities. And I'll show you why. So you don't have to use this. Use what you learn at CXC with that graph and pick out the numbers that satisfy the inequality. But let me show you when you better, you definitely have to revert to this, right? So you have to solve something like this now. This is a rational inequality. X plus 1 over x minus 5 is less than 0, right? Less than or equal to 0, sorry. Good. So what you're seeing here is you have a rational inequality and you don't have, at least now, last week I stopped where you were learning how to draw rational graphs, right? So I didn't go into it, right? I didn't go into it. So you have no clue what this thing looks like, right? You have no clue what it looks like. So what are you going to do, right? So the idea lies in you now using these critical values. So the critical values are -1 and +5. So you notice I divide the normal line, forget the y-axis, right? When I prepared these things, I had no way. Those times, I had all this fancy thing on the internet where I could have gotten a graph and subtract the y-axis, right? God knows how I got this one. If I don't know, got it from some textbook or something. Yeah. So I take the number line, I divide into the three sections: numbers less than -1, numbers between -1 and 5, and then from 5 and greater, right? And we're going to analyze what happens here, here, and here. I don't notice. Yeah. So I'm taking a number less than -1, right? I say, let x be -2. Put it inside the inequality. You get 1/7. And 1/7 is not less than 0, right? So no, these numbers less than 1 does not satisfy the inequality. We go between here now, between -1 and 5. So we take 0. We let 0 be representative of all the numbers between there, right? Put it in inequality and it works. Well, that tells you that yes, the numbers between 0 and 5 satisfies the inequality. And then we try the other part now. We try over here now. Try a number greater than 5. We take 6 and we put it in inequality and we get 7. And 7 is not less than 0. Therefore, the numbers greater than 5 does not satisfy the inequality. So our conclusion then is that our conclusion is x is somewhere between, I think, is somewhere between -1 and 5. I notice there's an equal sign here, right? But let me finalize that, right? When I show you the graph, right? When I show you the graph, whether we're going to put an equal sign there and an equal sign there. I'll tell you why just now, right? Let me just see the graph. Give me some time. Let me erase all this. So not because, I just want to point out to you, not because there's an equal sign here, mean that there's an equal sign have to be here. Like when you were dealing with quadratic and linear. I'll show you why sometimes it may not, you may not be allowed to put the equal sign here. Just give me a moment. Just give me a moment. Yeah. Okay, yeah, I do have this, but I'm not sure about the equal sign there. I'm going to explain why in a moment, right? And I'll tell you something, yes. So where am I? Yeah. Good. So watch this here. The inequality says that x plus 1 over x minus 5 can be less than 0 or equal to 0. Now, I want you to note here, I want you to note from the graph, right? That when you put in -1 here, the thing is equal to, is it equal to? Yes, watch. Down here, watch. -1 plus 1 over whatever, right? -1 minus 5. This is equals to 0, right? You all follow me? So the expression is equal to 0 when x equal -1. So yes, you can put equal to 1 here. Sorry, equal to -1. because it does satisfy the inequality. But come here now, where you're dealing with what we call an asymptote, where x equals 5, x equals 5 is an asymptote, meaning that the graph never crosses. This graph here, if we were to project it, never meets and crosses this line here. It's an asymptote, right? In other words, if you were to put 5 in here, you will get 5 plus 1 over 5 minus 5. Now this is undefined, right? And therefore, you see this part here where I got equal here? X can't be equal to 5. It can be equal to minus 1, but not to 5. Right? So when you see you got, all right, you get that the region that you're looking for is between minus 1 and 5. You must try the endpoints in the inequality to be sure, right? You have to try the endpoints just to be sure, because you don't know what the graph look like. And therefore, you will recognize that, oh, you know what? When x equals 5, we have an asymptote there, right? And asymptotes can be tricky. When I just started this job, I can remember telling the students that that's the answer, right? And later on, I said, you know what? Oh my! And by the way, a couple of batches of students went by, and then I recognized that, you know what? I didn't analyze this thing properly, right? So even me, I keep learning just like you. I don't know everything now nor ever, right? So that's an extra bit there. So you notice I have here that this is the answer, but no, every year I have to correct it now that this is your answer. X can be -1, but X can't be 5, because making it 5 will make this expression undefined. It wouldn't be 0 nor less than 0. It will be undefined. Right? Keep that in mind. Anybody follow what I'm saying there? That's heavy stuff, eh?
I follow it. I follow it.
I'm glad you follow it, man. At least somebody follow it.
Yeah, at least somebody.
Yeah. Yeah. All right, let's maybe take a, I don't know if this is the final one. Look at this one. Yes, this is the final example. So you got this horrible looking inequality there, right? And what you have to do here, you have to take the 1 over and make everything equal to 0 and so, right? So that's what I'm doing here, right? So 3x plus 1 over x plus 4 minus 1. And you do your little algebra and you reduce it and so, and you get this, right? Good. So you get 2x minus 3 over x plus 4 is greater than or equal to 0, right? Good. So what are we doing here? So we got our critical values, right? Our critical values from the numerator, let me see. For our numerator, we'll get 3 over 2. And for our denominator, you get -4, right? So again, we take our number line, break it up into 3 parts, right? 3 parts. All the numbers less than -4, all the numbers between -4 and 1.5 or 3 over 2, and then all the numbers greater than 3 over 2, right? And then you analyze what goes on, what's happening with the inequality. And this is the inequality you're using, right? When you take a number from here, when you take a number from here, and when you take a number from here, right? And what we'll find out, if you take your own sweet time, you'll figure out that, you know what? When you take a number less than -4, it satisfies the inequality. When you take a number from between here, no, it doesn't. But when you take a number from here, it satisfies it, right? That's why I have this as the solution. However, as I told you before, I did this when I was a little, fresh on the job. And then my mind grew when I found out that, you can't end here. And this, especially this part that makes up the denominator, I think this one is okay, right? If you were to take this value and put it in there or here, it's going to work. But if you choose -4, guess what? -4 is where the asymptote is. There's an asymptote there, right? And you can't have the equal sign here. So your answer is x is less than -4 or x is greater than or equal to 3/2. So keep this in mind. X is less than -4, not equal to. Because if you put x equal 4 in there, look at what happens. You get something up here over -4 plus 4 is undefined. You see that? So x can't be equal to -4. It can be less. It can be equal to. Right? So this is not your answer. This is not your answer. You got to drop out this equal sign here. For the reason that if you make x equal -4, you're going to have an undefined expression to evaluate, which is telling you that x equal -4 is an asymptote, right? So if you were to, you maybe go and draw this in Desmos, go and draw this. 2xy equal 2x minus 1 over x plus 4, you will see that there's an asymptote here. Let me do it. Let me do it for you and then show you, right? Let me write that down somewhere. Oh yeah, 2x minus 1 over x plus 4, right? Let me just go into Desmos. I'll stop sharing here for a moment. Give me a second, right? Desmos. I really love this program. So you're seeing this, right? So we're going with y equal, what was it? 2x minus 1 over, oh no, I think I did that wrong. I'll go with 2x minus 1, close bracket, over x plus 4, right? Good. So I just want to show you what's going on. Oh my. I want to do it wherever you can see -4. All right. I want to show you, okay. You see what's happening at -4 here? The graph is an asymptote, right? So, I mean, they can't show -4. Yeah, where -4 is, the graph is an asymptote. See that? It's an asymptote. So x can be equal to -4, right? I'm trying to show -4. Okay, -4 is here. The graph actually has an asymptote at -4. But at 3/2, where's 3/2? 3/2 is what, 1.5? 3/2 is somewhere. Did we get 3/2? But this is not 3/2. This is half. What are we getting here? You're supposed to get half, or what did we get here? X equal 3/2. Oh, wait. The thing is, x minus 3. When x is 3/2, that's 1.5. something is wrong with our solution here. Because from 0.5, the graph, did I get a right graph? No, man, we got a wrong value here. Why didn't even tell me nothing? It's 3x plus 1, 3x plus 1, yeah. From, yes. I'm trying to see where this is. 3x plus 1. Everything wrong here, man. It's 3x. No, it's 2x minus 3, man. Oh, gosh. Minus 3. No, I didn't even correcting me by.
Sir, I had the wrong thing. I
Yeah,
had 2x plus 1.
yeah. What did I have here? 2x minus 3. 2x minus 3 over x plus 4. All right, good. Yeah. So if you were to watch good, 4, you see where 4 is? Where minus 4 is? It's an asymptote. I can't, if I go down, you see that it's an asymptote. The graph is approaching it's approaching minus 40, but it's not never going to reach it, right? Coming down here, let me see what's happening at, yeah. This is like, okay, 1.5, right? So when it's 1.5, it's equal to 0. So that can be in the solution set, right? It can be in the solution set, but not minus 4. Minus 4 can't be in the solution set, right? So keep that in mind. It's just to illustrate something. Good. So, yeah. But you don't always have the luxury of the graph. That's what I'm trying to say, right? When you're in that exam room, you don't have Desmos with you, right? You don't have Desmos with you, so it's like physics. I remember when I was a kid doing physics, one of the first experiments we were encouraged to do is this: you put different objects inside of a box, and you have to figure out whether the object is, it's a solid, whether what is its shape. You understand? And that's what the physics and a lot of mathematics is all about, right? You have to figure out, you can't see the thing. You have to guess what's happening in there. You don't know what a graph looks like, right? So you have to figure out how is this graph behaving without seeing it, right? And that is why I can tell you what physics and chemistry, those subjects are so difficult, because you never really get to see what's going on. You have to assume that, you know what, because this thing is behaving so and behaving so, well, then the graph looks like this, you know. For those of you doing chemistry, you say, you know what, man, because this thing turned red or the thing turned green, you know that, well, maybe some copper sulfate is involved, or, based on the color of the thing, you have to assume that, well, you know what, there's some copper sulfate in this liquid here, when it turns a kind of reddish brown, you say there's some iron compound in there, right? You can only assume that based on the color. You can never say, I can see the thing. Oh yeah, watch iron floating here. No, you can't see it. You just watch the color and you assume that, oh yeah, that's what's going on here, right? In physics, when they have to figure out, well, what's the structure of the atom? There's nothing that can help you see the atom. At least what we have here in Guyana, right? They do have all these apparatus they have out here that can, you can actually go down to that level and have an idea of what's going on, right? They have to now theorize as to what the atom looks like based on, as I said, macroscopic behavior. And that's what we're seeing with this problem. You don't know what's going on really on the graph. You have to analyze what the numbers are saying. And then you know what? You suspect, you know what? There's an asymptote here, but there isn't an asymptote there. Right? Good. So yeah, I think I've covered quite a bit I've covered quite a bit in this lesson, right? So I don't want to do anything new after this, right? So I'm going to stop the recording here.